Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll continue our demonstration of various data processing utilities in Sklearn. The next utility is Add Dummy feature. Add Dummy feature augments dataset with a column vector. Each value in the column vector is 1. And you may remember that this is useful for adding a parameter for bias in the model. Let's take an example. Let's say we have a feature matrix. Here there are 2 features and there are 4 samples. We want to add a bias column with all ones in each of the features. So imagine that it's a dummy feature with 1 as the placeholder value. So we can add that dummy feature by using add dummy feature utility in sklearn.preprocessing module. So we simply call add dummy feature with the feature matrix as a parameter, and we get the transform feature matrix. And you can notice that in the transform feature matrix we have an additional dummy feature which is 1 that is added for every sample. Next, we'll look at custom transformers. So custom transformers enables conversion of existing Python function into a transformer to assist in data cleaning and preprocessing. It is useful when dataset consists of heterogeneous data types like raster images and text captions. The dataset is stored in, let's say, Pandas data frame, and different columns require different processing pipelines. We need stateless transformations such as taking log of frequencies, custom scaling, etc. So let's look at how these custom transformers are defined and used. So we use FunctionTransformer class from sklearn.preprocessing module. Here, in this example, we'll build a transformer that applies log transformation to features. For this demonstration, we'll use a wine quality dataset, again from UCI machine learning repository. It has got 12 different columns. So there are 11 features and one output column or one label column, which is quality. We read the dataset with read_csv function from Pandas, and we can see that there are 1600 or 1599 samples in this dataset. So we can obtain the count and other useful statistical properties of each feature using describe on the data frame. And we have transposed this in order to make it better readable on the computer screen. Now what we'll do is we'll apply np.log1p. So np.log1p returns natural logarithm of 1 plus feature value. So it automatically adds 1 to each feature value and then takes natural logarithm of that value. So we first instantiate a transformer with the desired function, and here it is np.log1p. You can also use any of your other function, custom defined function over here. Then what we do is we call transformer.transform on the dataset on which you wish to implement or you wish to apply this particular function, and that gives us a transform feature matrix. And you can see that in transform feature matrix, if we call the describe on transform feature matrix, the values, the statistical properties are now different from the original statistical properties. For example, mean of fixed acidity was 8.33. It has become 2.21 because we took log1p for each feature value. So here for your information, I have listed down a row on total sulfur dioxide. These are the statistical properties of sulfur dioxide in the original dataset and in the transformed dataset. So you can see that the mean has, in the log space, the mean is different, and then this is the minimum value and this is the maximum value, and these are different quartiles. So you can see that the values after transformation have indeed, the statistical properties have indeed changed. Next, let us discuss how to generate polynomial features for a given feature matrix. Let's say we have an input sample with two features A and B, and if you want to generate degree 2 polynomial, then what happens is that there will be additional features like A square, B square and AB and this particular one. So there will be 4 additional features that will be generated when we try to generate second degree polynomial features for the sample input with two features A and B. So we can get this particular feature representation with scikit-learn.preprocessing.polynomialFeatures. So let us try to use this particular class or utility on OneHotEncoder dataset. In OneHotEncoder dataset, what we are going to do is we are going to generate second order polynomial features. So we call or we instantiate polynomial features object with degree equal to 2. That means we want to generate polynomial features of degree 2. Before applying transformation, we dropped the label column or the target column from the Wine dataset. So next what we do is we call fit_transform. This is a transformation method, so we call fit_transform on the Wine dataset, and we get the polynomial representation of the data. So if we print the shapes of the feature matrix before and after transformation, you can see that in the original feature matrix we had 11 features, whereas in the transform feature matrix we have 78 features. There is no change in the number of samples or number of rows. So now after transformation we have 78 features. We will list out those features. We can list out these features by calling get_feature_names_out method on the polynomial feature object. So you can see the names of the feature. There is a special column 1 which is kind of a 0th order polynomial. Then there are original features, then there are 11 original features that are copied as they are, and then we have combinations of the features. So this is the square of fixed acidity feature, then there is a combination of fixed acidity and volatile acidity, and so on. So the features with ℓ2 suffix are degree 2 features of the input features. They are essentially obtained by performing or by squaring up the original feature value. For example, sulfate square is the square of sulfate feature. So values in the sulfates feature is squared up to obtain this particular feature. Then some features are combinations of names of the original features. For example, total sulfur dioxide pH is combination of two features, total sulfur dioxide and pH. Next, let us look at discretization. Discretization is also known as quantization or binning. It provides a way to partition continuous features into discrete values. In certain datasets with continuous features may benefit from discretization because discretization can transform the dataset of continuous attribute to one with only nominal attributes. OneHotEncoded discretized features can make a model more expressive while maintaining interpretability. So what we will do is we'll use KBinsDiscretizer class from sklearn.preprocessing, and we'll again demonstrate this on the Wine dataset. So we instantiate KBinsDiscretizer class with 10 bins, and we want to get OneHotEncoder encoded output from the KBinsDiscretizer, and we perform this particular discretization on the chlorides column. So we reshape the chlorides column into a matrix and then perform the transformation on it. So you can see that after performing the transformation, we have basically added a one-hot encoding vector with 10 components, and it will be 1 wherever the value in that particular bin is present. So what KBinsDiscretizer does is it takes range of values from chloride, divides it into 10 different bins, and for each of the bin it comes up with one hot encoding representation that you are seeing over here. We often need to convert categorical features into numerical features. There are various ways of doing that, such as using ordinal encoding, one-hot encoding, label encoding, or using dummy variables. So let's first understand each of these topics or each of these methods with examples. So for example, if we have a feature with state names like Punjab, Rajasthan and Haryana, so one way to encode this is by assigning a unique number, a unique integer number to each of these feature values. So for example, we can assign 1 to Punjab, 2 to Rajasthan and 3 to Haryana. But what happens, the problem with this approach is that it kind of induces some kind of an ordering where model might think that Rajasthan is 2 times Punjab because of the values over here, and that is kind of not really true. So if we do ordinal encoding, we might be inducing some undesired artifacts in the dataset, and that may not be useful for effective model training. So one of the common ways to handle such kind of features is using one-hot encoding. So in one-hot encoding, what happens is that we create a binary feature vector with number of components equal to unique values in the feature. So in this case, you can see that there are 3 unique values. So we create a new feature with 3 unique values. So there is new feature for Punjab, new feature for Rajasthan and new feature for Haryana. And wherever Punjab is present, the new feature corresponding to Punjab will have 1 in it and other features will be 0. So Punjab gets transformed into 1 0 0, Rajasthan gets transformed into 0 1 0. Notice that again the feature, since the value is Rajasthan, the new feature corresponding to Rajasthan is 1, others are 0, and same case goes with Haryana. So the third feature is set to 1 because that's a feature that corresponds to Haryana. So Sklearn has ordinal encoder as well as one-hot encoder, and they are part of Sklearn.preprocessing module. We'll demonstrate both of these utilities on Iris dataset. So Iris dataset has 150 rows. It has got 4 features and a class label, which is the type of the iris flower. So we again load the dataset from read_csv method. Iris dataset is again present as part of UCI machine learning repository. And what we'll do is, so all the values of the features are numeric. The label column is kind of categorical column. It denotes the type of the flower. So we can see that there are 3 unique labels here: Iris setosa, Iris versicolor, and Iris virginica. So what we'll do is we'll convert this label column into one-hot vectors. So we instantiate one-hot vectors with categories equal to auto, and we call fit_transform on the label set. But before doing that, we have to convert that into matrix, which is done with reshape command here. Let's look at the shape of the label vector. Before encoding, there were 150 150 rows in the label vector, whereas after encoding it has got 150. It has got the same number of rows, but there are now three additional columns. So we have converted this particular feature vector into feature matrix where each entry is a one-hot encoded vector. So we can look at first 5 entries, and first 5 entries belongs to iris setosa, which is which is the first feature in the new feature. This is iris setosa, this is versicolor, and this is virginica. So since all samples belong to setosa, you can see 1 in the first in the first column in the new feature in the new features that we obtained with one-hot encoding representation. Now what we'll do is we'll also use OrdinalEncoder and see the difference. So OrdinalEncoder has assigned value 0 to setosa, 1 to versicolor, and 2 to virginica, and you can see that the first 5 labels are all zeros. So here we are actually representing each label with a unique integer number, whereas here we are using one-hot encoding vector. We can also use LabelEncoder utility for transforming categorical features into integer codes. So LabelEncoder is also part of Sklearn.preprocessing module. We instantiate LabelEncoder called fit_transform with the desired input, which is iris labels in this case, and you can see that these iris labels are converted into numbers by the LabelEncoder. The output is pretty similar to what we got with the OrdinalEncoder. So first 50 values corresponds to setosa, then next 50 values corresponds to versicolor, and last 50 values corresponds to virginica. So there is zeros, there are first consecutive 50 zeros, 50 ones, and 52s. Sometimes we have multiple labels, and in order to convert those multiple labels, we use multi-label binarizer. So multi-label binarizer is again part of Sklearn.preprocessing module, and we call multi-label binarizer by, we instantiate multi-label binarizer here, and we call fit_transform method on multi-label binarizer with the desired input. In this case it is movie genre, and movie genre is again some kind of, there are multiple labels or multiple values associated with each column. It is a list of dictionary objects, and what happens is that this dictionary object is converted into some kind of a feature or a label matrix or some kind of a matrix. Let's not call it feature or label. This is generally, we are doing this on labels, so it might be useful to call this as a label matrix. And you can see that each value in the genre is kind of represents one column. So this is in a sense one hot encoding representation on multiple labels. So you can see that action is the first column. Action is present in the first, third, and fourth sample. So the first column corresponds to action, the second column corresponds to comedy, the third column corresponds to science fiction, and fourth column corresponds to thriller. So that's how the one-hot encoding representation is calculated for multi-label binarizer. We can also use getDummies features from Pandas data frame that converts categorical class variables to one-hot encoding. So here you can see that we have to of course specify what kind of prefix we want to use for one-hot new features. So here this particular prefix is used here: one-hot iris setosa, one-hot iris versicolor, and one-hot iris virginica. And these are unique values, if you remember, in the label column: iris setosa, iris versicolor, and iris virginica. So new feature name is derived with prefix and each unique value. And in getDummies, we also specify the name of the column on which we want to perform one-hot encoding. Let's look at composite transformers. There is often a case where we have basically features of different types, and since the features are of different type, they need different transformations. So we need to apply heterogeneous transformations to different columns. So column transformers help us to perform heterogeneous transformation on the feature matrix. So ColumnTransformer is part of a SklearnCompose module, and what we will do is we have this input feature matrix. It has got two features. The first feature is numeric, the second feature is categorical. On the first feature, we'll apply max absolute scalar. So we'll scale up the first feature using max absolute scalar. Then we want to again copy this particular feature for a reference that is specified by pass and pass through. And then we want to apply one-hot encoding on the categorical column over here. So we define a column transformer by defining different preprocessing that we want to carry out on different columns, and we call fit_transform method on column transformer. So now you can see that the output here, the first column in the transform matrix is the scaled version of the original features. Then we are copying the original features that comes from this particular statement, and then we have one-hot encoding representation. Those are last two columns. So the first column here corresponds to female and second column corresponds to male. We can also transform the target variable before fitting an estimator. So let's say if you want to transform a target variable before fitting a regression model, let's take an example of that. We will use California housing dataset for this demonstration. So what we are doing here is we are first defining a transformer that we want to apply on the label. So we are going to use max absolute scalar that will help us scale the output values or the output label. Then we define a linear regression model. So this is a linear regression object that we are instantiating, and then we call TransformedTargetRegressor, which is part of a SklearnCompose module, and we give an estimator or regressor as an argument, and we also give what kind of transformer that we want to use on the output. So we split the training data into training and test set, and we also define another linear regression object where we perform the fit on the raw data set. So we have now two regressors, one with the transformed target and second with the raw target. And you can see that the R square or R2 score for raw label regression and transformed label regression was the same. So now you might be wondering, when we use transform target regressor, we'll get output in the transform domain. We can convert that output in the original domain by using what is called as inverse transform.